Hello there, hello. And it's Tuesday morning, and it's start of a new day, and we're all happy to be here. I have no idea what I'm going to say when I start that when I hit that record button. Just I got to say something before I just launch into. Okay, let's do some physics. Okay, let's do some physics. We've been talking about temperature, kinetic internal energy, which is the sum of the kinetic energy of the individual particles that make up whatever object you've been examining. We've been talking about, and so we talked about this in terms of gases and the ideal gas law, and related gas laws came out as a consequence of this. And so now I want to turn our attention to solid objects. We're going to again ask the question, what happens to a solid object as its temperature changes, increases or decreases? And to, well, just to answer the question, with one limited though very important exception, the answer is what happens, well, the question is, what happens to a solid object as its temperature changes? The answer is the object either increases in size or decreases in size. Increases generally if the temperature increases, and decreases in size in its dimensions, is what I mean. Its length, its width, its height, when the temperature decreases. So, of course, now our goal is to figure out what is the specific physics that causes that to happen. What's the specific mathematical relationship that allows us to calculate how much that happens? Because it's physics. What do? We calculate. We love calculating. And is there any new information that we can glean from this this phenomenon? Okay, so the answer is, so the question is, what happens to a solid object and before I go any further, maybe I should define what I mean by a solid. For that matter, I never defined what I meant by a gas either. Actually, I did, but I didn't make a point of it, so let me make a point of it now. So, you're aware perhaps that there are three phases of matter. Generally speaking, there are actually four, but we will only deal with three of them. The solid phase, the liquid phase, the gas phase. As a general rule, and there are exceptions to this, but as a general rule, all materials are capable of existing in all three phases. And solid, liquid, or gas. A solid object is one where the molecules, or anyway the particles, I guess I should say, that make up your solid object have positions that are fixed, that they're fixed relative to the positions of the other particles of the object, and those positions on average do not change as the center of mass of the object changes position. Okay? So as long as the object is motionless, then the relative positions of all the particles that make up this book will stay in their fixed locations relative to each other. And as long as that's the case, we refer to this object as a solid. To the extent that that's not the case, the object either becomes a liquid or a gas. In a liquid, the the particles of the object no longer maintain a fixed distance from each other, but they move around with comparative freedom. Comparative to how much freedom they had when they were solids. Now, before I go any further, let me make sure you're clear. In a solid, I'm not suggesting that in a solid the particles of the object cannot move. That's not true. I carefully said that the average position of the particles don't change with respect to each other in a solid, average over time. So because the object is at some temperature above absolute zero, then the particles do have some kinetic energy, and they do move back and forth, but they tend to move in all three directions by equal amounts. And so averaged over time, the position of any single particle doesn't change. In a liquid, however, that is not true, and the positions of the particles do tend to change on average over time. However, they still have some force of attraction among the particles, and I guess I'm just not being clear today. Hey, it's Tuesday morning. We're just starting. In a solid, the reason the particles maintain fixed positions from each other is because they are exerting forces on each other. All the particles are exerting forces on all the other ones. All these internal forces tend to keep the particles at the same relative position, same relative distances from each other. However, in a liquid, those forces are considerably weaker, simply because now the particles have more kinetic energy than the energy provided by the forces, the binding forces among the particles. So the binding forces represent a certain amount of potential energy. They're not equal to potential energy, but they're related to internal potential energy. But if the kinetic energy of the particles is greater than that so-called binding energy, then the material will tend to be a liquid. The particles will move semi-independently of the other ones, but only semi-independently. They still exert significant forces on each other, and so as the particles move from place to place, the positions of one particle is still affected by the positions of the other particles. So the shape, the dimensions of the liquid tend to change only comparatively slowly over time. Compared to what? Compared to a gas. In a gas, the particles essentially are exerting no binding forces on each other, and every particle of the now gaseous object are moving independently of all of the other ones, except to the extent that they collide with each other. So, that all said, we've been thinking about gases so far, primarily. Now we're going to think about solids, and once we get through solids, we'll get to liquids. Okay. So that's what I mean by solid objects. Their positions of the particles are fixed on average over time. Okay. So what happens to a solid object as its temperature changes? And I've already said, as a general rule, as T increases, the dimensions of the object increase. And when the temperature of the object decreases, the object's dimensions, length, width, and height decrease also. So quite literally, when the temperature changes, the size of the object changes. Okay, that's fantastic. Next thing I'm going to do is, well, of course, ask the question, how much? Right? And we're going to take this by easy stages, 3 dimensions, of course, but let's take them one at a time. And so what we'll do to start out with is think about just the length of an object, and then we'll do length, and then we'll do 2 dimensions, and we'll finally do 3 dimensions. And it's not unreasonable just to think about just the length by itself. The issue here is when I have an object whose dimension, one of its 3 dimensions is much, much larger than the other 2. And we've encountered this kind of approximation before. In any case, so when that's a situation, then we can talk about just its length increasing or decreasing. Okay. All right. So We'll just start with length. I'm still not happy with these pins. All right. So the question now to ask is, what affects how much the length of an object changes when the temperature changes? Obviously, the bigger the change in temperature, we expect the bigger the change in length. And so that sounds reasonable. The change in length, we'll call that delta L, of course. Okay, well, first of all, the change in length should be proportional to the change in temperature. So the more you heat it up or the more you cool it down, the more the length changes. That seems reasonable enough. Second of all, the change in length should be related to what the object is made out of, the material that our object is made from. And it seems at least plausible to believe that plastic would respond differently to changes in temperature than steel, and steel would respond differently than glass, and glass would respond differently from wood, right? And so it seems like we should have to care about what the object is made out of. And then this one here, this is less obvious perhaps, and I'll try to justify it for you. The third thing, that the amount by which an object's length changes depends on how long the object was to start with, what its initial length was. Here's the idea, and here's the reason. The expansion or contraction of an object is a consequence of the fact that as you change the temperature of the object, that represents and indicates a change in the amount of kinetic energy of the constituent particles. Okay, but let's think about a temperature increase, for example. The object, whatever it is, just make a bar of something, bar of steel or something. Now, to our eyes, this just looks like a steel bar made of whatever it's made out of, well, steel, I guess. But it is, of course, on an atomic level, made up of lots and lots and lots of steel particles. Steel, I guess, is primarily iron and oxygen and a couple of other things. Okay, and like in all objects, these particles are in thermal motion. They have kinetic energy. All these particles are moving. Now, the object is a solid, and so they're not moving very far, but they are moving. And essentially what happens is that each particle is oscillating about some average position, okay? But it does move, okay? Each particle moves the way I'm sort of gesticulating here. But if I raise the temperature of the bar, that of course indicates that each particle has greater amount of kinetic energy, which means they're going to move faster and therefore farther from their average position. And they're still going to maintain their same average position, but their displacement in any one go is going to be larger. But that's true of all of these particles. And so all of the particles move, and in particular the ones out on the edges here. If all of the particles move through greater distances, then that means that the object as a whole gets bigger, because after all, the object is simply the collection of these moving particles. So the particles move more, the object takes up more space, it gets bigger. Okay? And of course, the reverse argument for it, if the if our bar here gets smaller. And so all of these particles are doing this additional movement when the temperature increases. And so the more particles there are, the more particles are pushing on other particles, and so the bigger the change in length ends up becoming. So that's our third point here. The third thing that how much the length changes depends upon is how long the thing was to start with. Its initial length. And it turns out that, at least to a first approximation, that's it. The amount by which an object's length changes, this is all it depends upon, and so that gives us the relationship that we're after. And so the amount by which an object's length changes, where we're only considering one of the dimensions, is calculated by multiplying the original length by how much the temperature changed, and then we're going to multiply it by another empirical constant, and this empirical constant represents the particular properties of the material from which our object is constructed. Okay, so steel is going to have one value for this constant, and wood is going to have a different value for this constant, and water is going to have, well, not water, but ice, I guess, would have a different value of this constant, and glass would have a different value of this constant, and tungsten would have a different value, and rubber would have a different constant, and so on. And this constant is given the symbol alpha, and alpha is called the, reasonably enough, a nice straightforward name, the coefficient of linear expansion. Okay. Again, it has its numeric value, depends upon the material that our bar is made out of, and its units is the inverse Kelvin. 1 over kelvins. Okay. So that's our starting idea, and so that's the important equation here, and I think this is a good place to stop this recording. In the next recording, I'll do a couple of examples.